All right, continuing our one-dimensional motion worksheet, working on practice 2E, which is number 11 and 12. So on number 11, it says a car traveling initially at 20 feet per second accelerates uniformly at a rate of positive 0.8 feet per second squared for a distance of 725 feet. So initial velocity, it said, was 20 feet per second. Acceleration it has at 0.8 feet per second squared, and for my distance or my displacement, 725 feet. And it says part A, what is the velocity at the end, or the final velocity? That's what we'd like to know. So again, if we go to our formula sheet that we have for this section, look at our equations, you notice the one thing we're missing that we've had before is time. They gave us no time. Every equation has time in it except this last one. This last one is if we combine the second one, which is really a derivation of the first, the second one with the fourth one. So we're just combining, substituting, solving this for time and substituting it in. I won't go through all that, just trust me, it all works. You can try it out if you want and see if it works for you. So we're going to use this equation, that VF squared equals VI squared plus 2A delta x. So final velocity squared equals initial velocity squared plus 2 times the acceleration times the change in position. We're solving for final velocity, so we're going to take the square root of both sides. It's the square root of the initial velocity squared plus 2 times the acceleration times the change in position. And now we have all those things. They're already converted to what we need. So it's just 20 feet per second squared plus 2 times acceleration, which was 0.8 feet per second squared, times the change of position, which is 725 feet. And then all of that is taking the square root of. You notice we have feet squared and second squared. Feet times feet is feet squared over second squared. Put the square root of it, and we're going to end up in feet per second. Now let's do our calculator. Where did I put? Over here. Plug our numbers in. So let's see if we can do all this at once. The square root of 20 squared plus 2 times 0.8 times 725, and we end up with 39.49, or 39.5 feet per second as my final velocity. In part B, it says what's the velocity if it accelerates for 375 feet. So now we're only going to go not quite as far, but my final velocity if my delta x is equal to 375 feet. Same equation, same problem. So final velocity is equal to the 20 squared. I'm going to leave out the units this time to make the numbers a little easier to see. Plus 2 times the 0.8 for the acceleration times this time 375 feet. And again, punch that all in. Square root of 20 squared plus 2 times 0.8 times 375. And we get 31.6 feet per second. Okay, so we aren't going quite as fast because we're accelerating, so we're going to get faster and faster and faster for every second that we travel, or for every foot that we travel. All right, that's 11. Let's look at 12. An aircraft has a liftoff speed of 100 feet per second. So on 12, my initial velocity is 100 feet per second. What minimum uniform acceleration does this require if the aircraft is to become airborne after takeoff run of 750 feet? Oh, so we're looking at acceleration. So it has a liftoff speed, so maybe we jumped the gun on initial speed because we're trying to take off. So it's like my airplane, right? We'll draw a little airplane sitting here. Right, he's sitting here down the runway. He's going to taxi down the runway this way. So really, he's sitting at rest to start. Okay, and he has to have liftoff. So at the end, before he's taking off, he has to have this 100 foot per second. So this is actually my velocity final. So sometimes it helps to draw your little picture. I just assumed, since it was the first one as a velocity initial, never can just assume, right? What acceleration? So that's my unknown. Does this require if the aircraft is to be airborne after takeoff run of 750 feet? And we said he's starting from rest because the aircraft is sitting there, right? We've all been on an airplane, or most of us, if you've ever been there, or at a stoplight or anything, it's the same thing. We're sitting there waiting to go, and then we start going. So my initial velocity is just 0. Again, we have that equation. There's no time, so we're going to use that same VF squared equals VI squared plus 2A delta X. Now, if we look, my initial velocity is 0. So before we start manipulating and moving variables around, 0 squared is just 0. So let's just get rid of that and say VF squared equals 2A delta X. And it makes my life much easier. That's one less thing I have to move around. So now I'm going to divide by the 2 delta X on both sides. And I'm going to end up with that acceleration. That's all that's left over here, right? Is equal to the velocity final squared over 2 times the change in position. So let's plug our numbers in. So acceleration is velocity final, which was 100 feet per second, squared over 2 times the 750 feet. And so we've got 100 squared, should be 10,000, there we go, divided by 1,500, but we'll do the math, 2 times 750. And we get 6.666 forever. Okay, so acceleration is equal to 6.67 feet per second squared. Right, because we have feet squared, second squared, and there's a foot down here, so that cancels out one of those feet, so we just have feet over second squared. And bing, bang, boom, we are done. I will finish the extension combination questions in the last video.